So we started object detection. I recently saw a very nice application, and that's for recycling composed versus non-composed objects. You can have a robot arm, uh, and that robot arm could be having some vision system powered by these object detection systems. And then if we forget about the mechanical part, which is about grasping objects, which is a totally different problem. And if we focus on the vision part, uh, you can have a classifier and an object detector that's going to detect composed versus non-composed, and then the robot arm is going to separate them one after another. So that's another application that you can keep in mind when we go through object detection. So we started with the metric, which is a totally different metric compared to what we are used to. It's not accuracy anymore. We are doing a different task, and we need a different metric to measure the performance of our algorithms. And in the end, we came up with mean average precision. And then we moved on to the algorithm, to one of the first algorithms, trying to solve object detection using deep neural networks and convolutional neural networks. And they were using a lot of PCs. And then the only part that they were using a deep neural network was the feature extractor. The rest of it, extracting region proposals and classifying regions, is what has been in the literature for a long time. So the only part was extracting features. So you don't need to do feature engineering anymore. And in the next papers, we are gonna keep moving towards an end-to-end training and end-to-end object detection. Basically getting rid of these region proposal algorithms like selective search and getting rid of the support vector machines, etc., and making everything end-to-end using deep learning. So let's start. We saw that a drawback of the last paper was that you needed to crop your image, either crop it or warp it, part of your image that was within your bounding box, because then you needed to push it through your neural network. And these neural networks needed, 270 something pixels by 270 something, or 224 pixels by 224 pixels as their inputs. So you have to either crop or warp and then push it through your neural network to get your features. So that's one problem. And the other one is that you needed to apply your convolutional neural network thousands of times, for instance, 2,000 times or even more. And these are costly networks. Why did you have to do that? Because you had multiple regions that are being proposed to you, and then you had to take that region, crop it or warp it, and then push it through your neural network, get your features, and then do your classification for that part of the image. So that was costly. This paper came along and said you don't have to actually crop and warp, and you can actually share a lot of computations by using spatial pyramid pooling. And we saw spatial pyramid pooling when we were doing semantic segmentation as well. So how is it going to work? You're going to change your classifier. This is your classification network. Up until this part, there is an input image, there is a convolutional layers, and then you're going to get your feature maps at some convolution, after some convolution, and that's going to be your input that we're going to work with. Then you're going to divide your inputs into bins. It could be the entire feature map, could be a single bin, or it could be 4 bins, or it could be 16 bin. So you create bins out of your last convolution layer, and then the rest of it is pooling. You just do an average pooling or a max pooling there. You just do average pooling or max pooling per each bin. The first one is going to give you 256 numbers. That's the size of this feature map. And then you're getting rid of your pixels. So that's going to give you a 256 dimensional vector. The next one is going to give you 4 of those 256 dimensional vectors. The next one is going to give you 16. And then you concatenate all of them together. And then you can push it through your fully connected network, through the rest of your network. The cool thing is that this vector is now fixed dimensional. It has a fixed length. This pooling could have different sizes, but it doesn't matter because you're in the end gonna have 1 plus 4 plus 16 of them, and you're pulling on different sizes for your bins, so you can have different sizes of the pixels here, pixel dimensions. So let's say A by A is the feature map size that you end up with after your conv5. For instance, for VGG, it's going to be 13 by 13. And let's say you want to divide that feature map into n by n bins, for instance, 2 by 2, like here. Then you're going to define your window size, and the window size is going to be adjusted automatically. It's a function of A and N, the ones that you chose. That's going to give you your window size. That's going to be the window size of each one of these bins. And the stride is going to be the floor. That's the ceiling. This is the floor of A over N. So maybe some pixels are going to have overlap, but the overlap is very small when you do your striding. So this is how you're going to implement that. That was the classification network. And the advantage of that is that now you can input images of variable sizes into your network. So you don't have to input 240, 224 by 224 anymore. You can put any sizes for your images and push it through your network and do your classification. That's from the classification side of things. But when you go to object detection, something interesting happens. On your input image, there is a box. You can take that box and project it into your feature. And that's going to correspond to a window on your feature map. So you begin with the box, you push that box through your convolutions, and that's going to give you a window. You don't even actually have to push the box through your convolution operators. You can just compute that window where it's going to be located, because it's a rectangular grid and things are going to be nice. You can actually compute the size of this. But then what you're going to do is take your image, push it through your convolutions only once, and that's the part of the computations that you're saving. You push it through your convolutions only once. You take that window, this you compute. It's very easy to compute that. Once you have that window, you do your spatial pyramid pooling. It's going to give you a fixed length. This is going to be your features that you're going to use through the rest of your algorithm. So what you need to do now is just do your computations from this point on. So that's the computational cost per region proposal. And you're pushing your operations, you're saving a lot of computations by only taking one image and pushing it through your convolution. So this part of the computation is saved. The rest of it is going to be repeated multiple times. So does this make sense, what we are saving and where we are saving computations?
And this is different than what we just talked about on the right there, where in that case we were looking at the whole feature map, but now we're looking at a sub window of the feature map.
Exactly. So this one was some modifications that you had to do to be able to input images of any size to your network, because this is going to be your backbone. Then you train that on ImageNet, and then you're going to do some transfer learning here.
Okay.
But then once you're here, this window, you can compute it. For instance, if you know the down sampling size of your convolutions, so it's very easy to compute this window. Once you have that window, you can take a look at your feature maps and then compute features per each window that you might end up with. And the rest of it is the same as before.
And this fixed length representation is the same dimension, whether it's a representation of a window or whether it's a representation of the entire image.
Exactly.
And you can just do then like the window with the ceiling and the floor division just gives you a different value.
Exactly.
Okay, perfect.
So the cool thing is that this fixed length representation doesn't depend on the size of on the pixel size of the input. It's always going to have that length.
As long as our window isn't smaller than like 16 pixels or something. Or I guess you could add padding in that case and still do it.
Yes. So the problem might happen when you have very small objects. Then you might have some trouble. You might lose in terms of your evaluation metric. That could be a drawback. But it's worth it. You're saving a lot of computation. Because previously you had to take that part of the image, crop it or warp it, push it through your convolutions multiple times, thousands of times. Now all you need to do is push it once, push the entire image through your convolution only once, and then do your computations from this point on multiple times after the window, after the convolution.
And is this window still being determined by that search we talked about in the previous paper?
Yes, so everything is the same as the previous paper, except for this part,
Okay.
that you're sharing computations. And these are some of the results qualitatively. You can identify the bus and the car and locate them. And in terms of numbers, mean, average, precision, this is doing very good, and it's much faster compared to RCNN. And it's much faster because of the amount of computations that you're saving.
Computational savings comes here because you push an image through and find the feature map only one time, and then you just subsample that to get these fixed length representations a whole bunch of times. And before, you would subsample first and then push the subsampled image through a convolutional neural network.
Exactly. So you first have to crop part of the image, and then warp it, crop and warp, and then push it through your convolution.
Yes, you're evaluating the network itself like tens of thousands of times for all the different croppings.
Yes, and remember, we want these algorithms to be fast because we want to apply them on video data. And there is a frame rate per second that these algorithms have to be fast. So our CNN wasn't that fast. So it wasn't practical for real cases. So you needed to save computations to make the algorithm useful. Okay.
Is this also called ROI pooling? Because I've seen that name.
No, that one is what we are going to cover now. So I needed to cover the previous one first to convey some ideas of why we are doing what we are doing. Now, fast RCNN is going to build upon the ideas that you just saw about spatial pyramid pooling. It's going to have a similar idea, and it's going to be about ROI pooling.